Today we're going to discuss the derivative as a function. Now you may recall from last time that f prime of a gives the slope of the tangent line to y equals f of x at x equals a. Today we look at f prime of x, which is a function of x. It gives the slope of the tangent line to y equals f of x at any x for which that slope exists. So constant, function of x. The definition of f prime of a is the lim as h goes to 0 of f of a plus h minus f of a over h. The definition of f prime of x looks almost identical. The difference here is that x is now allowed to vary. Let's see what that looks like graphically. Here's a picture of y equals f of x. And to find f prime, we need to be looking at slopes of tangents. So what we've done here is drawn in the tangents to the curve at various points. You can see here at -1, the slope is positive. At 0, the slope is in fact 0. At 1, the slope is negative. At 2, it's 0 again. And at 3, it's positive. So what we do is we calculate these slopes and then we plot them on the graph of y equals f prime. So you'll see here this slope is a little bigger than 4. This slope is 0. This slope is a little bigger than -2. This slope is 0. This slope is a little bigger than 4. And these 5 points lie on the graph of y equals f prime. If we were to do this for every point on y equals f of x, we would get a picture that looks like this for y equals f prime. Now note the correspondence. Here, the function is increasing. Slopes are positive. Here, the function is decreasing. Slopes are negative. Here, the function is increasing again. Slopes are positive. Now we calculate the derivative of functions using the definition. So for example, let's take a look at f of x equals x squared, and we want to calculate f prime. The definition, f prime of x is the lim as h goes to 0 of f of x plus h minus f of x over h. F of x is x squared, so f of x plus h becomes x plus h squared. Here's your minus x squared over h. Oh, important little note here, we actually have to do a calculation here, because if you put in h equals 0, what you're going to get on the top is x squared minus x squared, which is 0, and 0 on the bottom, 0 over 0 indeterminate form. So we actually have to do something here. Now what we have to do, however, is actually pretty easy. We just have to square this term, and we get x squared plus 2xh plus h squared minus x squared over h. The minus x squared cancels the x squared, and we're left with 2xh plus h squared over h. Now you'll notice there's a factor of h in the top. We can factor it out. We get this h over h term, which is what we're always looking for in these situations, because that's going to be 1 in the limit. And then here's the term we can handle. 2x plus h, when h is 0, that becomes 2x. So we pick up 1 times 2x, or just 2x. Now the advantage of this calculation is that we've done it once, we don't ever have to do it again. We now know that if our function is x squared, its derivative is 2x. Now let's look at f of x equals the square root of x and calculate f prime. Same idea, we look at our definition. This time f of x is the square root of x, so we're getting the square root of x plus h minus the square root of x over h. Now here what to do is not so obvious. There's no multiply out, there's no factoring, there's no find a common denominator. What does work, however, is multiplying top and bottom by the conjugate of this. and the conjugate is x plus square root of x plus h plus x. And we multiply by this term because it's 1 and it does not change the value of this. However, it does simplify matters considerably. Now, why does this work? If you think of this as a and that is b, this is a minus b times a plus b. We know that's a squared minus b squared, and that's going to get rid of the square roots. So what we end up with is the square root of x plus h squared, which is x plus h, minus the square root of x squared, which is x, and then in the denominator we've got h times this square root of x plus h plus the square root of x. Notice that on the top we have x minus x, and we've just got to get an h. Here's our h over h again. We factor it out, and we've got something that's going to be 1 times a term we can deal with. Because as h goes to 0, this becomes 1 over the square root of x plus the square root of x, which is 1 over 2 square roots of x, and that's the derivative. Suppose f of x is 3x plus 4. Let's calculate f prime. Now, we're not actually going to use the definition here. We're going to observe that the derivative is 3. Why is that true? The line y equals 3x plus 4 has a constant slope of 3, and the slope of the tangent line for a line is exactly the slope of the line. So if you've got a linear function like this, the derivative is going to be constant, and that constant is going to be the slope. Not all functions are as well behaved as the ones we've just looked at. So for example, let's look at f of x equals absolute x and calculate f prime. So remember that the absolute value of x is x when x is bigger than or equal to 0, and is minus x when x is less than 0. So if x is greater than 0, absolute x is x. Y equals x is a line with slope 1, so the derivative there is 1. If x is less than 0, absolute x is minus x, so f prime of x is minus 1 because y equals minus x is a line with slope minus 1. What happens at 0? Well, if x equals 0, we've got two different definitions on each side, so we're going to have to take one-sided limits. The limit as h goes to 0 plus of f of 0 plus h minus f of 0 over h equals the lim as h goes to 0 plus of absolute h over h. It's positive, so it's just h over h, so the limit is 1. On the other hand, the lim as h goes to 0 minus ends up being absolute h over h, and now absolute h is negative h because h is negative. This limit is minus 1. That means the two-sided limit does not exist because these numbers are different. F of x equals absolute x has what we call a corner at x equals 0. It's continuous, but the derivative doesn't exist because the limit from both sides is not equal. And here's a picture of what a corner looks like. Over here, the slope is 1. Over here, the slope is minus 1. When does f prime not exist? Let's take a look at the following graph. And remember that f prime is the slope of the tangent. So if we zoom a section of the curve and we don't see something that looks like a line, there isn't a tangent line, which means that any sort of a discontinuity is going to cause trouble. So if we look at x equals 2, we see there's a jump discontinuity. If we think about what f prime looks like here, you can see that on this side at 2, the function's increasing, but the slopes are getting smaller and smaller, so we get a picture that looks sort of like that. On the right-hand side, we have a line with a negative slope, so the derivative is going to be constant at that negative value, and this is what f prime is going to look like at a jump discontinuity. At a removable discontinuity, here, as we said previously, this is a line, the slope is constant, except at the discontinuity, there's no derivative. At x equals 5, we have what's called an infinite discontinuity. If you look on the left-hand side, you can see that the slopes are huge and positive. If you look on the right-hand side, you can see that the slopes are huge in magnitude and negative. And this is what f prime is going to look like at an infinite discontinuity. But there are places where the function is continuous and there's no derivative. So when we call something like that a corner, here's an obvious place here. If you zoom in on this, no matter how close you zoom, you are not going to get something that looks like a line. In fact, what we see is on the left-hand side here, we're on this little line segment which has the negative slope, which we've got right there. And now at the corner, suddenly the slope has jumped to positive. So we get a graph that looks like this at a corner. And then the last place is when there's a vertical tangent. And now there actually is a tangent line here. It's just vertical. And remember that the derivative is the slope of a tangent, and vertical lines don't have any slope. What happens here is as we come close to 1, the slopes get huge and positive. On the other side, they're still huge and positive, so we have a picture that looks like this. Now let's sketch the graph of f prime of x based only on the graph of f of x. Now in such situations, you want to look for places where you know the derivative exactly, and such places include horizontal tangents, and if they're on the graph there are line segments. Those will be good because we know that the slope of that segment will be the derivative on that entire segment. Okay, so we start with the horizontal tangents. We can see that there's a horizontal tangent at x equals 3. There's a horizontal tangent at x equals 6, which means that 3, 0 is on f prime because the derivative at 3 is 0, and 6, 0 is also on the graph of f prime. Now, we look at the line segments, and we can see the segment for x less than 0 passes through minus 2, 0 and 0, 4. So the slope is 4 minus 0 over 0 minus minus 2, or 2. The section of the graph between 0, 4 and 2, 2 is also a segment. The segment between x equals 0 and x equals 2 has slope 2 minus 4 over 2 minus 0, or minus 1. And we notice at 0, there's a corner. There is not a corner at 2, by the way. So f prime of 0 does not exist. And we end up drawing the following graph. Here, we're x less than 0, and we said there the slope of our graph was 2, so the derivative is 2. Between 0 and 2, the slope of that graph was minus 1, so the derivative has value minus 1. And we have the 2 points that we already know about. Now, between x equals 2 and x equals 3, we can see that the derivative is negative, but it gets less negative as we approach 3, which means that the derivatives are going to be negative, but increasing towards 0, and that gets us this sort of a shape. Now, between x equals 3 and x equals 6, the slopes are positive, and they get bigger for a while, and then they get smaller again down to 0 when we get to 6, and that gets us this sort of shape. And then finally, when x is bigger than 6, we have negative slopes, and they get more negative as we head off this way, which gives us this picture. And that's a fairly accurate sketch of the graph of f prime.